So today I'll be talking about TCP/IP and TCP/NC, which is a newer version of it. So say you're me and you're a comp sci and you're using the internet. It really doesn't matter why you're on the internet, but what does matter is that you're currently using a network. Networks are cool, and if you read the linked blog post and listen to our unplugged example, then you should understand most of the relevant information, but what I'm here to talk about today is packets. Not packets of paper, those are boring, but packets of data. Packets of data are pretty much virtual mail packages. They have an address stamped on top of them, as well as some cool contents called a payload. The payload contains data, be that a Word document, a picture, a sound file, or something else entirely. To understand how data is transferred from one location to another, first we need to understand how the internet actually works. Transfers of data occur within a framework called an OSI, or Open Systems Interconnection. Within the context of the internet, this framework is called a TCP/IP, or Transmission Control Protocol with Internet Protocol. TCP/IP divides neatly into 4 layers: application, transport, internet, and link. There is also a 5th layer called physical, which deals with the actual electrical interactions within the computer sending and receiving data. But I'm not going to talk about that now. We'll start with the lowest level and build up. The lowest level is the link level, which you may know as more common name is Ethernet. The link level contains the local area network that you are working on, and is what allows transfer of data from one node in your network to another. The next level up is the IP, or internet level. The internet does not handle what happens within the local networks. It is solely concerned with the formation of connections between LANs. The connection of networks is called an internetwork, or alternatively, an internet. The third level is the TCP, or transport level. This level is where actual transfer of data occurs. This governs the actual formation of data packets. It takes the provided data and adds an address to it, and then pushes the data packets into something called a data stream. This ensures that the order is correct upon receipt. The final level is called the application layer, which simply runs how the rest of the layers function. For most web pages, HTTP, or Hypertext Transfer Protocol, is used to set up and run the underlying layers. To summarize, you open a web page, which will then send a request from data to your router, which will then send the request to data to other routers until it reaches the source of the data, and that connection will form and the data packets will be transported through the network just formed to your web browser. Unfortunately, this can have several side effects, including long loading times. One consequence of this setup is that you can lose packets. Now, packet loss means that a select portion of the requested data fails to make it to the intended destination. The primary way that networks deal with packet loss is through brute force. They resend the data over and over again until it's all received. For example, TCP will either have the receiver request a resend of all data, or the sender can resend any data that is not acknowledged or ACK'd by the receiver. Fortunately, this isn't particularly efficient and is one of the primary causes of a slower internet connection. Thankfully, MIT has come to the rescue. A paper titled Modeling Network-Coded TCP Throughput, a Simple Model and Its Variations by Kim, Maydard, and Barros discusses the possibility of adding equations to data packets within a stream so that the receiver of the stream can quickly identify which packets are missing. The results are pretty astounding. By adding an equation that takes up 10 bytes of data to a 1.5 kilobyte data packet, one can increase the rate of transmission by over 10 times, or 1,000%. And this is applicable on any server, no matter how high the chance of losing a specific packet is. It has no effect on networks with no loss. Obviously, no matter how you code the data, if it always gets there, it doesn't matter. But it does significantly improve the performance on lossy wireless networks because it lacks the potential to time out should enough consecutive data packets become lost. And in this way, I think that's kind of cool, and that's it.